For nearly a century, scientists believed they had mapped the structure of Earth's deepest interior with confidence. The model was clear: a solid inner core composed primarily of iron surrounded by a liquid outer core. This understanding was not speculation. It was built from seismic evidence collected over decades and supported by physics under high pressure. And then the measurements began to diverge. Seismic waves generated by earthquakes travel through Earth at measurable speeds. There are two primary types relevant here: P waves, which compress material, and S waves, which shear it. In a perfectly solid inner core, both should travel in predictable ways based on known properties of iron under pressure. But observations show something unusual. P waves travel faster along the polar direction than along the equatorial plane. The difference is measurable, on the order of a few percent, indicating that the inner core is anisotropic. It has direction-dependent properties. This alone suggests a structured, possibly aligned internal arrangement. More striking is the behavior of S waves. In solid iron under core conditions, S waves should travel relatively quickly. Instead, they move significantly slower than expected and lose energy as they pass through the inner core. This attenuation indicates that the material does not resist shear in the way a typical solid should. Quantitatively, this is reflected in the Poisson's ratio of the inner core, estimated to be around 0.44 to 0.45. For most solid metals, this value ranges between 0.2 and 0.3. A higher value means the material resists compression strongly, but deforms more easily under shear stress. This is a measurable physical property derived from seismic data, not an assumption. The conditions at the inner core are extreme. Pressures exceed 330 gigapascals, more than 3 million times atmospheric pressure at the surface. Temperatures are estimated between 5,000 and 6,000 degrees Celsius, comparable to the surface of the Sun. Under these conditions, iron exists in a dense crystalline phase, likely hexagonal close-packed, but its mechanical behavior deviates from what standard solid-state models predict. These are not isolated observations. Independent seismic studies using different earthquake data sets and analysis techniques converge on the same conclusions: directional wave speeds, reduced shear velocity, and high attenuation. A useful teaching insight here is that when multiple independent measurements point to the same anomaly, the focus shifts from questioning the data to re-evaluating the model. So we are left with a precise, evidence-based contradiction. The inner core shows structural order consistent with a solid, yet mechanical responses that resemble something less rigid. To understand how such conclusions are drawn from vibrations alone, we now turn to the methods that make it possible to study a region nearly 6,400 kilometers beneath our feet. If the inner core presents a contradiction, the next step is not to guess, but to ask a more practical question. How do we know anything about a place no one has ever reached? The distance alone makes direct exploration impossible. Earth's center lies nearly 6,400 kilometers beneath the surface. The deepest borehole ever drilled reaches just over 12 kilometers. That is less than 0.2% of the journey. Beyond that depth, temperature, pressure, and material strength make further drilling unfeasible with current technology. So the entire structure we discuss is not observed directly. It is inferred. Unlike space, where telescopes provide images, Earth's interior offers no visual access. It is completely opaque. Light cannot travel through it, and no instrument can send back pictures from those depths. Instead, scientists rely on a different kind of signal: vibrations generated by earthquakes. When an earthquake occurs, it releases energy in the form of seismic waves. These waves spread outward in all directions, passing through different layers of the planet. Each layer alters the waves slightly. Some speed them up, others slow them down. Some bend their paths, while others absorb their energy. This process is similar to how medical imaging works. In a CT scan, X-rays pass through the body, and differences in absorption reveal internal structures. In Earth science, seismic waves play a comparable role. The difference is scale. Instead of centimeters, we are measuring across thousands of kilometers. There are two main types of waves used in this analysis. P waves, or primary waves, compress and expand the material they move through. They can travel through solids, liquids, and gases. S-waves, or secondary waves, move by shearing material side to side. These can only travel through solids. This distinction is critical. When S-waves disappear or weaken, it signals that they have entered a region that cannot support shear, typically a liquid. When they reappear, it suggests a return to solid material. By placing sensors across the globe, scientists record the arrival times and strengths of these waves after earthquakes. With enough data, they reconstruct paths through the Earth, much like tracing routes on a map. Over time, these paths form a detailed picture of internal layers. A useful teaching insight is that this method does not rely on a single event. It depends on thousands of earthquakes recorded over decades, each adding a small piece to the overall model. The reliability comes from consistency across independent observations. It is through this indirect but rigorous approach that scientists identified boundaries, transitions, and anomalies deep within the planet. And it is through the same method that the contradictions in the inner core first became impossible to ignore. With this foundation in place, we can now examine the discoveries that originally defined Earth's layered structure and understand how those conclusions were reached. Once scientists learned how to read Earth through seismic waves, the next step was interpretation. Patterns in the data were not random. They pointed to boundaries, clear transitions where material properties changed. The first major breakthrough came from noticing something subtle but consistent. Certain waves were arriving earlier than expected. In 1909, Andrija Mohorovičić examined seismic records from an earthquake and found that some waves had traveled faster along deeper paths. This could only mean one thing. Beneath the surface layer, there existed a denser region where waves could move more quickly. That boundary, now called the Mohorovičić discontinuity, marked the transition between the crust and the mantle. A useful way to understand this is to imagine sound traveling through different materials. Sound moves faster through steel than through air because the particles are more tightly packed. Seismic waves behave in a similar way. When their speed changes abruptly, it signals a change in material. A few years later, in 1914, Benno Gutenberg identified a far more dramatic shift. He observed that S-waves, which require solid material to travel, were completely absent beyond a certain depth. This was not a gradual weakening, it was a clear disappearance. The implication was unavoidable. A large region inside Earth did not support shear motion. In physical terms, it behaved as a liquid. This region became known as the outer core. Its existence explained not only the absence of S-waves, but also specific patterns in how P-waves slowed down and bent as they passed through it. Independent observations confirmed the same structure, reinforcing the conclusion. Then came a discovery that refined the picture further. In 1936, Inge Lehmann studied faint seismic signals that appeared where none were expected. These signals suggested that some waves were being reflected or refracted by a deeper boundary within the liquid core. Her interpretation was precise. Inside the liquid outer core, there existed a smaller, solid region. This was the inner core. A teaching insight here is worth noting. None of these scientists could see what they were describing. Each conclusion depended on careful reasoning from indirect evidence. The strength of their work lies in consistency, different data sets analyzed independently, leading to the same structural model. By the mid-20th century, these findings combined into a coherent framework, a layered Earth with distinct physical states at different depths. It was a model built step by step, each layer revealed through changes in wave behavior. For decades, this structure explained nearly everything scientists observed. It became the foundation of modern geophysics, and because it worked so well, it was rarely questioned. But as measurements became more precise, small deviations began to appear within this very model. The structure remained, but the details no longer aligned perfectly. And it is within those details that the current mystery begins to take shape. With this layered structure in place, the Earth began to look understandable. A solid crust at the surface, a slowly flowing mantle beneath it, a liquid outer core, and at the center, a solid inner core composed largely of iron. Each layer had distinct physical properties, and together they explained a wide range of planetary behavior. This model was not just descriptive, it was predictive. The movement of tectonic plates, the rise of magma, even the existence of Earth's magnetic field could be explained through interactions between these layers. The liquid outer core, for instance, circulates due to heat and rotation, generating electric currents. These currents, in turn, produce the magnetic field that surrounds the planet. A useful way to visualize this is to think of the Earth as a system rather than a stack of isolated layers. Heat flows outward from the core, material moves in response, and each layer influences the next. When a model can explain multiple independent phenomena, confidence in that model naturally increases. For many years, this framework remained stable. It was tested against new seismic data, refined in detail, but never fundamentally challenged. The inner core, in particular, was treated as a dense, rigid sphere, compressed into solidity by immense pressure despite extreme temperatures. However, improvements in measurement began to reveal something unexpected. As seismic instruments became more sensitive and global networks expanded, researchers could detect finer variations in wave behavior. These were not large discrepancies. They were subtle shifts, small differences in speed, direction, and energy loss. At first, such variations were attributed to noise or local irregularities. That is a standard scientific approach. When a model has strong explanatory power, minor deviations are often treated as secondary effects. But over time, these deviations showed consistency across different regions and independent studies. A teaching insight worth noting is that consistency across independent measurements is difficult to dismiss. When separate data sets, collected under different conditions, point toward the same irregularity, the explanation must move beyond experimental error. The deeper scientists examine the data, the more these inconsistencies accumulated. The overall structure of Earth remained intact, but the behavior of waves within the inner core did not fully match the expectations of a simple solid iron sphere. This marks an important shift. The question is no longer whether the layered model is correct in broad terms. It is. The question is whether the inner core, as currently described, captures the full reality of its physical state. To address that, we must look more closely at the signals themselves, specifically how seismic waves behave as they pass through the deepest region of the planet. It is in those details that the next layer of understanding begins to emerge. As the inconsistencies became too consistent to ignore, attention shifted from the model itself to the signals passing through it. The focus narrowed to a simple question: what exactly are seismic waves telling us about the inner core? When earthquakes generate waves, those waves do not move uniformly in all directions. Instead, their speed and behavior depend on the material they travel through. By measuring these differences precisely, scientists can detect patterns that reveal internal structure. One of the most reliable observations concerns P waves. These waves, which compress material as they travel, move through the inner core at different speeds depending on direction. Specifically, they travel faster along paths that pass near Earth's poles than along those closer to the equator. The difference is small, but measurable, typically a few percent. This indicates that the inner core is anisotropic, meaning its internal structure is not uniform in all directions. A simple way to picture this is to think of wood. It is easier to split along the grain than across it. The material is the same, but its internal alignment changes how force moves through it. The inner core appears to have a similar directional property, though under far more extreme conditions. There is also evidence of variation across regions. Seismic data shows subtle differences between the eastern and western hemispheres of the inner core. These are not surface features, but deep structural variations, suggesting that the core is not perfectly symmetrical. But the most puzzling signals come from S waves. As discussed earlier, these waves depend on a material's ability to resist shear. In a solid iron core under immense pressure, S waves should travel efficiently and maintain their energy. Instead, they behave in a way that contradicts this expectation. They move more slowly than predicted and lose energy as they pass through the inner core. This attenuation suggests that the material does not fully resist deformation. It yields, at least partially, under shear stress. A teaching insight here is that wave speed is not just a measurement, it is a direct expression of how a material responds to force. When wave behavior deviates from prediction, It points to a mismatch between assumed and actual physical properties. These observations, directional differences in P waves, regional variations, and unusually slow, weakened S waves, are consistent across multiple studies. They do not cancel each other out. They reinforce the same conclusion: the inner core is not behaving like a typical solid. At this stage, the question becomes more precise, not whether the core is solid or liquid, but how it responds mechanically under extreme conditions. To answer that, we must examine the fundamental properties that govern how materials deform and transmit energy. To move beyond observation, we need to examine how materials respond when forces act on them. Seismic waves provide the evidence, but the explanation lies in mechanics. At its core, the question is simple: how does the inner core deform when stress is applied? There are two fundamental ways a material can respond. It can compress, meaning its volume changes under pressure, or it can shear, meaning its shape changes without a change in volume. These responses are not abstract concepts. They directly determine how seismic waves travel. P waves depend on compression. They push and pull material in the direction of motion. If a material strongly resists compression, P waves move quickly through it. S waves, by contrast, depend on shear resistance. They require the material to hold its shape while layers slide slightly past one another. If the material cannot resist this motion, S waves slow down or disappear. The key parameter that connects these behaviors is known as Poisson's ratio. It measures how a material balances compression and shear. In most solid metals, this value falls between 0.2 and 0.3. Such materials resist both compression and shear in a relatively balanced way. The inner core does not follow this pattern. Seismic data indicates a Poisson's ratio close to 0.44 or 0.45. This is unusually high. It means the material strongly resists being compressed, yet offers much less resistance to shear deformation. A simple comparison helps clarify this. Imagine pressing a rubber ball and a block of steel. The steel resists both compression and shape change. The rubber resists compression but deforms more easily in shape. The inner core behaves closer to the second case, despite being composed primarily of iron. This creates a mechanical paradox. Under pressures exceeding 330 gigapascals, iron should become extremely rigid. Its crystal structure should lock into place, making deformation under shear difficult. Yet the observed wave behavior suggests that, at least partially, the material yields. A teaching insight here is that material properties are not fixed. They depend on conditions. Pressure, temperature, and atomic structure can shift behavior in ways that are not intuitive based on surface experience. What we consider a solid at normal conditions may behave very differently under extreme environments. The high Poisson's ratio, combined with slow and attenuated S waves, points toward a material that is neither fully rigid nor freely flowing. It occupies an intermediate mechanical state, structured yet flexible. This brings us to a critical question. Can known forms of iron, even when mixed with other elements, account for this behavior? Or does the explanation require a different way of thinking about matter itself? The next step is to test the conventional possibilities and see where they fall short. If the inner core does not behave like a typical solid, the next logical step is to test the most reasonable explanations within known physics. Scientists did not immediately turn to new theories. They began with familiar possibilities, adjusting known materials and structures to see if the observations could be reproduced. One of the first approaches was alloying. The inner core is primarily iron, but it is unlikely to be pure. Lighter elements such as carbon, hydrogen, oxygen, or silicon are expected to be present in small amounts. When these elements mix with iron, they can alter its mechanical properties, making it less rigid and more deformable. At first glance, this seems promising. Laboratory studies show that alloyed iron can exhibit increased flexibility under certain conditions. However, when these models are pushed to match the extreme pressures and temperatures of the inner core, they fall short. They can reduce rigidity slightly, but not enough to explain the significantly slow and attenuated S waves observed in seismic data. Another idea focused on structure rather than composition. Instead of a single, uniform crystal, the inner core might consist of many small grains, tiny crystals packed together. In such a granular structure, the boundaries between grains could allow slight movement. Under stress, these grains might shift, rotate, or slide past each other, reducing overall resistance to shear. This is not an abstract concept. Materials like sand or packed ice behave this way on a macroscopic scale. They can appear solid, yet internally rearrange under pressure. Extending this idea to the inner core, scientists proposed that thin layers of melt could exist between grains, acting as lubricants that further reduce rigidity. But again, the numbers do not fully align. To match the observed seismic behavior, the amount of melt or the degree of grain movement would need to be very specific and consistently maintained across the entire inner core. Such conditions are difficult to justify under the known thermal and pressure gradients. A teaching insight here is that a good scientific explanation must account for all major observations simultaneously. Explaining one feature while ignoring others is not sufficient. In this case, alloying explains some flexibility, and granular models explain some deformation, but neither explains the full set of seismic anomalies. As more variations of these models were tested, the same conclusion kept emerging. Each explanation could solve part of the problem, but none could resolve it completely. The mismatch was not minor, it was systematic. At this point, the investigation reaches a turning point. When all conventional explanations fail to reconcile the data, the question changes. Instead of adjusting known models, scientists must consider whether the state of matter itself behaves differently under extreme conditions. This shift does not happen easily. It requires setting aside familiar categories and exploring less intuitive possibilities. Yet the data leaves little room for alternatives. If the inner core is neither behaving like a standard solid nor a simple mixture, then a fundamentally different explanation must be considered next. With conventional explanations exhausted, the problem changes form. The question is no longer how to adjust known materials, but whether the inner core exists in a state that does not fit traditional categories. This is where a more unconventional idea begins to take shape. Scientists propose that under extreme pressure and temperature, matter may organize itself in a hybrid state, neither fully solid nor fully liquid. This state is known as superionic. To understand this, consider how a typical solid is structured. Atoms are arranged in a fixed lattice, each one vibrating around a stable position. In a liquid, those atoms move freely, constantly changing position. These are the two standard models we rely on. A superionic material combines both behaviors. One set of atoms forms a stable, solid lattice, maintaining overall structure. At the same time, another set of atoms moves freely through that lattice, almost as if it were a liquid embedded within a solid framework. A simple analogy can help. Imagine a rigid metal cage filled with small beads. The cage holds its shape, but the beads inside can move in all directions. The system as a whole is stable, yet internally dynamic. This is a simplified picture, but it captures the essential idea. In the case of Earth's inner core, the lattice is thought to be formed by iron atoms. Within that lattice, lighter elements, such as carbon, may move more freely. These mobile atoms do not break the structure, but they do change how the material responds to stress. This model offers a direct explanation for the observed seismic behavior. The solid lattice allows P waves to travel efficiently, maintaining the appearance of a structured medium. At the same time, the movement of lighter atoms reduces resistance to shear, slowing down S waves and increasing energy loss. A teaching insight here is that states of matter are not limited to the familiar three. Under extreme conditions, new phases can emerge, defined not by simple categories, but by how particles interact at the atomic level. Computer simulations support this possibility. When iron-carbon systems are modeled at pressures above 300 gigapascals and temperatures of several thousand degrees, they begin to exhibit superionic behavior. The resulting properties, anisotropy, reduced shear velocity, and high Poisson's ratio, closely match what seismic data reveals. This alignment is significant. For the first time, a single model can account for multiple independent observations without requiring unlikely conditions or fine-tuning. However, simulation alone is not enough. A model must be tested against reality. The next step is to ask whether such a state can be recreated, even briefly, under controlled laboratory conditions, and whether it behaves as predicted. If the supersonic model is to be taken seriously, it must move beyond simulation and into experimental testing. This presents a significant challenge. The conditions inside the inner core, pressures above 300 gigapascals, and temperatures of several thousand degrees are not easily reproduced. They cannot be sustained in ordinary laboratory setups. Instead, scientists rely on brief, controlled extremes. One of the most effective methods involves high-velocity impact experiments. In these setups, small samples of iron mixed with lighter elements, such as carbon, are subjected to intense shock waves. These shocks are generated by firing projectiles at extremely high speeds, often exceeding Mach 20. The impact compresses the material within microseconds, reaching pressures and temperatures comparable to those deep inside Earth. The key is not duration, but intensity. Even a fleeting state, if measured precisely, can reveal how the material behaves under those conditions. To capture this behavior, researchers use a technique called photon Doppler velocimetry. This method tracks the motion of a material's surface with extreme precision by measuring changes in reflected laser light. From these measurements, scientists can infer how waves move through the sample, including their speed and how quickly they lose energy. A simple analogy may help. Imagine tapping a solid object and listening to how the vibration travels. A rigid material produces a clear, sharp response. A more flexible one produces a slower, dampened signal. In these experiments, the same principle applies, but at far higher speeds and pressures. The results are telling. Under core-like conditions, the tested materials show reduced shear wave velocity and increased attenuation. In addition, the inferred mechanical properties correspond to a high Poisson's ratio, consistent with values derived from seismic observations of the inner core. This alignment between experiment and observation is critical. It suggests that the unusual seismic signals are not artifacts or measurement errors. They reflect genuine physical behavior that can be reproduced under controlled conditions. A teaching insight here is that validation in science often requires convergence from different approaches. Theory, simulation, and experiment must point in the same direction. When they do, confidence in the explanation increases substantially. It is important to note that these experiments do not recreate the entire inner core. They isolate key properties under similar conditions. Yet even this partial reproduction is enough to test whether the proposed state of matter behaves as expected. For the first time, there is experimental evidence that supports the idea of a supersonic-like state in iron-rich materials under extreme conditions. The mechanical response observed in the laboratory mirrors what seismic waves reveal on a planetary scale. With this, the explanation moves from possibility to plausibility. The next step is to consider what this means, not just for seismic anomalies, but for the broader behavior of Earth itself. With experimental results now aligned with seismic observations, the question shifts from possibility to implication. If the inner core behaves as a supersonic system, then its role within the planet must be reconsidered in practical terms. The inner core has often been treated as a passive structure, dense, stable, and largely unchanging. But a material that allows internal movement, even within a solid framework, introduces a different kind of dynamics. The presence of mobile atoms within a rigid lattice means that the core is not simply resisting forces, it is responding to them in more complex ways. One immediate consequence relates to directional wave behavior. Earlier observations showed that P waves travel faster along polar paths than along the equator. A supersonic structure offers a natural explanation. If atomic motion varies with orientation or flow patterns within the lattice, then wave speeds will also vary depending on direction. What appeared as an anomaly becomes a predictable outcome of internal structure. There are also implications for regional differences within the inner core. Variations between eastern and western hemispheres may reflect differences in composition, temperature, or the distribution of mobile elements. In a purely solid model, such variations are difficult to sustain. In a partially dynamic system, they become more plausible. Perhaps the most significant implication concerns Earth's magnetic field. The field is generated primarily by motion in the liquid outer core, where conductive material circulates and produces electric currents. However, the inner core influences this process by affecting heat flow and boundary conditions. If lighter elements such as carbon can move within the inner core lattice, they may contribute to energy transfer in ways not previously considered. Even subtle internal motion could affect how heat is distributed at the boundary between the inner and outer core. Over long timescales, this can influence convection patterns in the outer core and, indirectly, the behavior of the magnetic field. A useful teaching insight is that large-scale planetary effects often depend on small-scale physical properties. The way atoms move under extreme conditions can shape processes that extend thousands of kilometers. It is important to remain precise here. The supersonic model does not replace the layered structure of Earth. The inner core remains structurally solid in a broad sense. What changes is how that solid behaves under stress, and how it interacts with its surroundings. This refinement illustrates a broader principle in science. Models evolve not by being discarded entirely, but by becoming more detailed and more accurate as new evidence emerges. The earlier model was not wrong, it was incomplete. What began as a contradiction in seismic data has led to a deeper understanding of matter under extreme conditions. It reminds us that even within our own planet, there are states and behaviors that challenge simple classification, and this has implications beyond Earth. Similar pressures and temperatures exist in other planetary bodies. Understanding these states here provides a framework for interpreting distant worlds. The journey inward, it turns out, is also a journey outward, toward a more complete picture of how matter behaves across the universe.